You already have this written down, so just relax for a little bit. When I give you a formula that you are going to prove using induction, your first step is to show that when you plug in 1, it's true. And then your second step, which is a long step, is to use algebra to show that k makes k plus 1 true. Okay? So first step, easy peasy. Second step is going to be a lot of algebra, but as long as we get a grasp of the process, the algebra is not difficult. Okay? I don't think you need to write this down either. Okay? But what happens in our 2-step proof? You know what? I'm going to have you write this down. I like it. Okay? So this takes those 2 steps and kind of breaks it down for you. Okay? First, we're going to verify the formula is true when n equals 1. Okay? That's about as straightforward as you can get. Plug in 1. Doesn't work. Okay? And you need to show me, like I need to see that you plugged it in and then you evaluated that both sides are equal. Okay? Then step 2, the first thing you're going to do, and you're going to write this word, assume the formula is true for n equals k. So basically you're going to write the word assume and then change all of your n's to k's. So I want you to think about something. If this is the 9th partial sum for the sequence, and I know what it equals, if I want the 10th partial sum, all we would have to do is take that 9th partial sum and add the 10th term. Would you agree? Like all we would have to do is take these 9 numbers we've already added together and add the 10th number. Okay? So what we're going to show is that our k plus 1 sum is the k sum plus the next term. If I have the k sum, then the k plus 1 sum is just adding on the next term. My goal is to do 2 proofs together here in class. Your assignment has 5 proofs. You are not doing 5 proofs in your homework tonight. Maybe I'm going to have you look at number 11, and then the other 4 we will do in class tomorrow. Okay? So let's do 1 proof and see what it looks like. Oh my. There we go. So we're going to use mathematical induction to prove the following formula. So go ahead and write down this formula. We are adding up the terms of the sequence 2n minus 1. And our shortcut, however many terms there are, is the same as n squared. So on the left we have a sum of a sequence. On the right we have a shortcut, n squared. Now, being able to read and follow your work is important. Your neighbor being able to read and follow your work is important. Your work should be so nice and neat and organized that even somebody in Algebra 1 could figure out what you are doing. Okay? Somebody who doesn't know mathematical induction should be able to at least figure out what's going on with your work. Okay? So what is our first job? Okay? We need to make sure that S of 1 is true. Okay? So what's our first term? 1. And then if we go to the other side, does that equal when I plug in 1? 1 squared. Does 1 equal 1 squared?
Yes.
Okay. All we did, we took the first term and then we plugged in 1. Are those the same? All right. Our second step. What's the word we need to write in our second step? Assume. This is the one time you get to assume. All right. And we are going to copy paste, except all of the n's turn to k's. We're talking about, so n stands for all positive integers. When we change it to k, we're basically saying, hey, let's pick a random number somewhere in the sequence. Okay? N is talking about all the numbers. K, we're picking out a specific number without actually giving it a numeric value. Okay? Okay. So here's where our practice from earlier is going to come in handy. That right there, well, yes. This right here is P sub k. We did a whole bunch of practice writing P sub k plus 1. So let's do that, but we're going to skip a lot of lines. If I plug k plus 1 into this, it becomes k plus 1 squared. If we can show that the k plus 1 sum is k plus 1 squared, we are done. So all that work we just did in our homework, you took this and we wrote it here. Okay? Well, let's talk about what that k plus 1 sum would look like. If I'm talking about the k plus 1 sum, then we are going to add everything from the k sum, and then we are going to add the k plus 1 term. How did I get this right here? I took this, and my next term is the same thing with k plus 1 plugged inside.
Is that second 3 supposed to be a 5?
Yep, that second 3 is supposed to be a 5. Talking and writing at the same time sometimes. Okay. So our k plus 1 sum is the same thing as the k sum, but we add an extra term. All right? Well, ladies and gentlemen, do we know what this is right here? Same thing as that, right? So we can say, all right, our sum is really k squared plus this guy that I wrote in red. Okay. If I rearrange this, oh, I don't have to rearrange at all. What's k squared plus 2k plus 1 factor 2? We did it. And your algebra should work out every time. But you basically need to finagle your algebra until you get to that k plus 1. The piece of k plus 1 like we were doing in our home. Okay. And once we get there, we say, therefore, S of n is true for all positive integers. Give me a conclusion, like what did we just do? We just proved S of n is true for all positive integers. Okay. We're going to do one more proof so you can see this again. And then what do I want you to do before I see you tomorrow? Only which problem? Only number 11. That is it. Okay? All right. Let's try this one right here. And I'm doing it with you. I'm just giving you a chance to write it down. The first step to our proof is proving that it is true for 1. So what is our first term? 5 is our first term. Does that equal when I plug in 1 to the other side? So I took our first term, is 5. I took this over here and I plugged in 1. Does it work? Cool. I need to see the work of you plugging that in. I don't want just 5 equals 5. I want to see this step right here. Okay. Now our second step, what word do we write? Assume. And then we're going to rewrite our formula, but with k's instead of n's. Okay, this right here, let's think about it with k plus 1 plugged in. What would it be? K plus 1 times k plus 5. We are trying to get there with our k plus 1 sum. So I'm going to skip a few lines and write s sub k plus 1 equals k plus 1 times k plus 5. And let's talk about the k plus 1 sum. Okay? The k plus 1 sum is the same thing as the k sum, but we're going to add the next term. We literally copy paste, but then we add another term because we have one more term in our sum. I'm underlining this in green. What does that equal? Okay, we already know that that equals k times k plus 4. And our red term turns to 5 plus 2k. Okay, and here's where your algebra needs to make sense. What we can do is we can distribute this to be k squared plus 4k plus 5 plus 2k. And after we would do that, we would combine like terms to be k squared plus 6k plus 5. And what does k squared plus 6k plus 5 factor to? This right here. Kaden was question.
Since it's 3 plus 2 times k plus 1, wouldn't it be 5 times 2k?
Well, this would distribute through, so we would have 2k plus 2.
Oh, okay.
Okay, and then don't forget to conclude. Therefore, S of n is true for all positive integers. Now, I know that this is a little rough, and I do not expect perfection for number 11, but I want you to try it. And only number 11. We will talk about and go through number 11 in the morning tomorrow, and then the rest of the time we will work on the other 4 problems. Does that sound good? What are you going to do tonight? Number 11. Is it okay if it doesn't go well? Yes. Just do your best to limp through it, okay?